Hello everyone, and welcome back to this series on intermediate probability theory, and today we're going to be working through some more change variable derivations of statistical distributions. In particular, this time we're going to be focusing on the t distribution. But before we get into that, let's just set up a couple of foundational theory that you definitely should know, because the t distribution probably is one of the more difficult ones to derive compared to the other main ones. So we're going to start with the standard normal distribution, which we know is 1 over square root of 2 pi e to the minus 1/2 x squared, sometimes known as a Gaussian distribution, with x ranging from minus infinity to infinity and having this bell-shaped curve as its shape. And then we have the chi-square and chi random variables, which are derived from the sum of squared standard normal random variables that are independent, and then the chi being the square root of the chi-square distribution, having these particular probability density functions. And of course, supported on 0 to infinity, having that skewed right shape in terms of their density. Right? So once we have this, now we're going to set the stage on how we're going to define a t random variable. So what we're going to do is we're going to suppose that xk is a sequence of IID, n of them, normal random variables with mean mu and standard deviation sigma. Then, if you're familiar with basic statistics and that story, then a test statistic for assessing the value of a mean is always going to be the point estimate, an unbiased point estimate, x bar, minus the claimed value of the mean, let's call it mu, all divided by sigma divided by the square root of n. And it's very easy to prove that this is going to follow a z, also known as a normal 0-1 distribution. Right, so again, the main point about this z test statistic is we have x bar, which is a random variable, we have mu, which is a number, and then sigma, which is the population standard deviation, which is a number, and then we have the square root of n, which of course is a number. So the main thing that differentiates a z test statistic from what people refer to as a t test statistic is the bottom. So it's still going to be equal to x bar minus mu all over something, a standard deviation over the square root of n, but now we're going to have s. And that's going to be the random variable associated to the standard deviation of a sample. Right? So here, x bar is a random variable, mu is a number, s is now a random variable, not a number because it depends on the sample and hence is a random variable, and now we have a number. So a z-stat is a random variable over a number, and a t-stat is a random variable over a random variable, right? So this is a random variable in particular for the standard deviation, which is pretty much a chi random variable. Now, in terms of what that degrees of freedom is for a chi, that sometimes is not obvious to see. But nonetheless, if xk is a sequence of IID normals, then what we have here virtually is a normal divided by a chi with some scalar in front of it, right? So what is the quotient of a normal and a chi random variable up to scalars? This is going to follow some distribution, and the distribution's name is going to be referred to as a t distribution. Some people also call it a student's t distribution, named after one of the people who designed it. All right, so a couple theoretical things that I leave to you to verify, definitely fun. So let's assume that xk, again, is a sequence of n IID normal random variables, not necessarily standardized. So mu being the mean, sigma squared being the variance. Then the following identities are going to hold. In particular, n times x bar minus mu, the quantity squared, all divided by sigma squared, will be associated to an x bar, a chi 1 squared distribution. And why is that the case? Because you might think, well, doesn't x bar have a bunch of normal variables in it? Yes, but they're not standardized, right? So x bar technically is one normal. Mu is its mean because the expected value of x bar is still going to be equal to mu. And the variance of x bar is going to be sigma squared divided by the square root of n, which is technically in this expression, it's just rearranged. So technically x bar is our one standard normal random variable, and it's standardized with respect to its mean and standard deviation. So this is indeed a chi-square 1 random variable. And if you take a bunch of them, in particular the sum from k is equal to 1 to n, of xk minus x bar, the quantity squared, and then scale it by the population variance, sigma squared, one should be able to show that this is going to follow a chi-square n minus 1 distribution. And this is a very, very important identity because this helps us build inferences on the population variance and also population standard deviation. Right? So from this is kind of where the sample variance definition is defined, at least up to some scalar parameter. So s squared, again, is commonly defined as the sum from k is equal to 1 to n of xk minus x bar, the quantity squared, all divided by m minus 1. And if you don't remember why we divide by m minus 1, that's to ensure that the expected value of s squared is equal to sigma squared. So if we take this object and divide and multiply by sigma squared, you should be able to show that that's going to be a chi-square n minus 1 times sigma squared all over n minus 1 distribution. All right? And that's going to be what we refer to as a scaled chi-square random variable. And from this is how we usually build the test statistic for variance, in particular nu times s squared all over sigma squared, following a chi-square m minus 1 distribution, where this number nu will be equal to n minus 1, which is sometimes referred to as the degrees of freedom of that chi-squared random variable. So this is just some things that if you've taken statistics, you definitely should have seen already, but we'll use a couple of these things in our derivation of the t distribution. All right? So how are we going to start? So we're going to be starting with y being equal to z all over x over square root of n. So the expected value of z is equal to 0, so we don't need to do z minus 0 here. And then our square root of n we're just going to put on the top of our expression, right? So that square root of n is just accounting for the sample size or the scaled chi random variable that we have in this picture. Right? So we're going to define y to be equal to this quotient of random variables, and our goal is to find the density function for y. So here we're starting off with variables x and z. X is going to be my chi-square, or my chi n random variable, and then that z in particular is n minus 1 random variable, and z, that's going to be my standard normal random variable n0, 1. So once we have this, we're going to perform a change of variables here into new variables y and u. And then we're going to try and figure out, okay, I don't really want this variable u, so I'm just going to condition off that variable u in order to get just my value of y. And that's going to give my probability density function. And the variable u I'm going to choose is just going to be my chi random variable x. Right? So we're going to start with x and z. We're going to map to y and u, and then we're going to map to y via conditioning. All right? So once we have this, then we can start performing some change of variable tricks. So solving the very first equation for, let's say, z, we can find that x times y will be equal to z times the square root of n, and this is going to force z to be equal to xy all over the square root of n. And if we solve u equals x for x, then you can clearly see that x is going to be equal to u. Again, we're going to be going to the yu world, so you should only see yu on the right-hand side of this equation. So we have xy, but x is the same as u, so we're just going to write this as uy all over the square root of n, and that's obviously just going to be equal to u for our transformations. So z goes to uy over root n, and x goes to u, and that's going to be our transformation. Now we need to build our Jacobian for our transformation. So the Jacobian of our transformation is going to be what? So keep in mind the Jacobian is going to be equal to, at least the Jacobian matrix, will be equal to xy, xu, zy, zu. Right? So our variables were coming from x, zz, partially differentiated with respect to the variables we're going to, y, uu. Right? So once we have that, then we can just differentiate our expressions. So what is the derivative of x with respect to y? Well, x doesn't have any y's in it, so the derivative of x with respect to y will be equal to 0. Notice that x does have a u in it, so the x with respect to u's derivative will just be equal to 1. And then what is the derivative of z with respect to y? Well, z with respect to y just has u over the square root of n in it as a coefficient. And then what is the derivative of z with respect to u? That's just going to be the same thing, just with y. So that's going to be y all over the square root of n. Right? So therefore, the determinant of the Jacobian matrix is going to be equal to what? So that's going to be 0 times y all over the square root of n minus u all over the square root of n times 1. And that's going to give us minus u all over the square root of n. And that's going to give us our Jacobian. All right? So therefore, once we have our Jacobian and our transformations of variables, then we can say the following via change of variables theorem. So the joint probability density function between y and u with respect to little y and little u will be equal to the joint density function between x and z of little x, little z, times the absolute value of the Jacobian minus little u all over the square root of n. All right? So we have this as our change of variables relation. Now, how do you find the joint probability density function between a chi variable and a z variable? Because if they're independent random variables, then you can just multiply their marginal density functions and be done with it. But are they really independent necessarily? Well, there's a theorem that helps us out here. So if xk is a sequence of independent and identically distributed normal random variables with mean mu and variance sigma squared, then the covariance between the sample mean x bar and the sample variance s squared will be equal to 0, implying that these two variables, x bar and s squared, are independent. And you might be thinking, well, what does that even mean in this regard? Well, keep in mind x bar is associated to our normal random variable, and s squared is associated to our chi squared random variable, and there's our normal variable standardized, and there's the square root of our chi squared. And you should be able to prove that if, x squared is independent of, for example, z, then x will also be independent of z up to linear transformations and also nonlinear transformations. So since we have normality as our premise for both x and z, we can say that fxz can be decomposed into the product of its marginal density functions. All right? So once we have that, then we can proceed with our setup. So fyu will be equal to fxx, so that's going to be our chi squared, multiplied by fzz, that's going to be our standard normal, times the absolute value of our Jacobian, which is going to be u divided by the square root of n. All right? So that is our setup. So there's our chi variable, and there's our standard normal random variable. So let's just go ahead and plug in our probability density functions. So our chi, or let's start off with our normal, I guess that's a little bit more easier, is going to be 1 over the square root of 2 pi times e to the minus 1/2 z squared. So it's the probability density function for z, multiplied by, now let's do our chi density function. So again, that's 1 over 2 to the n over 2 minus 1. Chi squared doesn't have the minus 1, but chi does. And then we're going to have our gamma n over 2 coefficient, multiplied by e to the minus 1/2 x squared. Keep in mind, chi squared doesn't have squared, but chi does in its PDF. And then we're going to have x to the power of n minus 1, and keep in mind it's n minus 1 for chi, n over 2 minus 1 for chi squared. And then don't forget your lonely little Jacobian, u over the square root of n at the very end. So once we have that set up, then it's just a matter of simplification to prep up for our calculus sequence. Okay? So if we want to rearrange this in a clean way, you might want to throw your square root of n and your square root of 2 pi underneath a constant. At least that's what I'm going to do. So that's going to give us 1 over the square root of 2 pi m times e to the minus 1/2. And note, we have a couple e to the minus 1/2 terms. We have this term here, we have that term there. So technically we could combine this, but keep in mind we need a function of y and u only, so make sure that you do that as soon as possible. So if we do that, we're going to have e to the power of minus 1/2 z squared, but z is the same as uy all over the square root of n squared. And then we're going to have times 1 over 2 n over 2 minus 1 gamma of n over 2, and then times e to the minus 1/2. Again, we don't want x, but x is equal to u, so we're going to write that as u squared. And then x is going to be the same as u, so we're just going to write that as u to the power of n over 1. N minus 1, but keep in mind that's u, and u to the n minus 1 times u will just be u to the power of m. So let's just delete that minus 1 there, and then that gives us our simplified answer. Right? So once we have that, then we can start simplifying as we need to, or set up for our integration step. So I'm going to write this instead as 1 over 2 to the n over 2 minus 1 gamma n over 2 square root of 2 pi n multiplied by u to the power of m multiplied by e to the power of minus 1/2. Let's combine our exponents and write that as y squared over n plus 1 times u squared. Right? So once we have that, that gives us our probability density function, joint probability density function between y and u. And keep in mind our target is y, and remember u is associated to a chi n random variable where little u belongs to the interval 0 to infinity. So that's going to be our approach for conditioning off that variable of u. So how are we going to do that? So again, fy, our marginal density function for y, will be equal to the integral over the domain of the variable that we are conditioning over of fy u little u with respect to the variable we are deleting off. Right? So that's the beginning of our removal of the variable u. It's important to note that this constant in front of this integral term right here doesn't depend on anything about u and anything about y. So since it's not going to really be playing a part with the primary integration process, I'm just going to call that constant k, just for the time being, just to make the next few series of calculations a little bit more easier to follow. So once we substitute our probability density function with this new constant k taken into consideration, we're just going to have k times the integral from 0 to infinity of u to the power of n times e to the power of minus 1/2 1 plus y squared over n times u squared du. All right. A couple of things that are important to note here is that this constant here, without the negative sign, is always going to be greater than or equal to 0. So if we can let that be equal to v, which we will, then we can try and force a gamma function representation for this integral here. So we're going to be letting v be equal to that positive constant, 1/2, 1 plus y squared all over n times u squared, and then we're going to differentiate with respect to u. All right, so once we do that, we're going to have dv will be equal to, so the 2 is going to come down, cancel with that 1/2, and then inside of the brackets, if we get a common denominator, we're going to have n plus y squared all over n times u times our differential of u. Also from here, we can see that du will be equal to, once you rearrange, n all over u times n plus y squared. Right? And that will be your differential of u substitution piece. It's also important to note that v can be transformed into 2v to be equal to m plus y squared all over n times u squared, and this will come in handy also once we start transforming. Because if you solve for u squared in this expression, u squared will be equal to 2vn all over m plus y squared. And then from here, you can get an expression for u by taking the square root of both sides. And since u is always positive, we can just take the principal square root of that, giving us u is equal to 2vn all over m plus y squared, all to the power of 1 over 2. Right? So that's going to be our transformations to do our u substitution, and then we can move on with our integration strategy. Right? So once we have that, what are we going to have? So fy of y will be equal to our constant in front times the integral from 0 to infinity. And then we're going to have our u to the power of n, but u is going to take this form now. So we're going to have 2vn all over m plus y squared, all to the power of n over 2, times e to the power of minus that positive number, for which we called v. And then we're going to have our differential term, which I will organize as n over m plus y squared, multiplied by m plus y squared all over 2vn to the power of 1/2 dv. Right? So that's going to be our integral, and now we're just going to shift things around. Keep in mind this is an integral with respect to v, so anything with y only can come out. Anything that doesn't have v or y can also come out. So we can write this integral instead as fyy is going to be equal to our constant k times a lot of different moving pieces. So from our first bracket, we can grab a 2 to the n over 2 term. We're also going to have an n to the n over 2 term located there. Located on the top of that differential of u term, we're going to have another m. And also in that differential of u term, we're going to have an m plus y squared to the power of 1 over 2. And that's going to organize our numerator. On the bottom, we're going to have an m plus y squared to the power of n over 2 from that leading term. And then we're going to have an m plus y squared located from that du term. We're also going to have a 2 to the power of 1/2 from that last term there. And we're also going to have an n to the power of 1/2 from the same exact term. Then we're going to have an integral from 0 to infinity. And then we're going to have v to the n over 2 minus 1 over 2 once you simplify. And then e to the minus v dv will give you your integral setup for your gamma function transformation. So once we have that, then we can bring back our k from before, and we can write this as 1 all over gamma n over 2 times the square root of 2 pi. That's not going to change. Let's group our 2 stuff together and our n stuff together. So our 2 stuff is as follows. So we're going to have 2 to the n over 2 all over 2 to the n over 2 times 2 to the minus 1, 2 to the minus 1/2, and 2 to the minus 1/2. And then let's group our n stuff together. So we're going to have n to the n over 2 times n all over n to the minus 1/2. And then we're going to have some more n stuff. Let's write it as m plus y squared to the power of 1/2 all over m plus y squared to the power of n over 2 plus 1, and then multiplied by our lonely little integral from 0 to infinity, v to the n over 2 plus 1 over 2 minus 1, e to the minus v dv. Now let's start with this 2 bracket. Notice that everything in this bracket cancels with itself, and that's just going to be equal to 1. That's actually very beautiful. This last integral is just a gamma function, so we're just going to throw that in the front with its gamma friend. And then we're going to have, let's just write this instead, fyy will be equal to gamma n over 2 plus 1 over 2 is just the same thing as gamma n plus 1 all over 2. And then we're going to have gamma n over 2 times the square root of n pi. That's n pi, not 2 pi. And then let's look at our n coefficients, just the n coefficients on the top. In particular, n to the power of n over 2 plus 1 over 2 all over n plus y squared all to the power of n over 2 plus 1 over 2. Notice that they have the same exact exponent, which means you can combine those fractions, simplify, throw a negative sign on the top, and then you're going to have fy. Y will be equal to gamma n plus 1 over 2, gamma n over 2, square root of n pi, as our leading coefficient, times 1 plus y squared all over n, since the n over n cancels, and then minus m plus 1 over 2. And that, my friends, is our t distribution. In particular, Tn distribution. Again, that n refers to as the degrees of freedom, or sometimes the scaling parameter of the distribution. You might be thinking, what does this distribution look like? If you've taken statistics, you definitely should know. But it has practically the same shape as a normal distribution. I want to draw it a little bit more scaled so you know at least one important difference between the t and the normal. So in terms of the t versus normal, the t distribution will tend to have fatter tails than that of the standard normal distribution. So that's why I've kind of made my tails a little bit more wider on the left and right for a t distribution. And yes, it is symmetric about 0. All right. Some theorems that you should know. So if a random variable is a t, if Tn is a t random variable with n degrees of freedom, then the following things are going to be true. The expected value of a Tn random variable being 0 should not be super hard to prove because you're going to have, when you have this even function times x, that's going to give you an odd function on a symmetric interval, that's going to give us 0. You could also try and find the second moment and then prove that the variance of a Tn random variable will be equal to n divided by n minus 2. And a very important and very beautiful property is the limit as n goes to infinity of Tn will be equal to the z distribution. You should at least be able to see that that's the case from the expected value invariance formulas, because 0 goes to 0 as n goes to infinity, n over n minus 2 goes to 1 as n goes to infinity, and that normalness, the expected value in the variance formulas going to a standard normal parameter value, definitely makes a lot of sense, but definitely try and prove this last property because it's very, very important. And one last other thing before we go today, notice that this expected value of Tn is equal to 0. This is actually only going to be analytically true when n is bigger than 1. When n is equal to 1, you'll actually see that the expected value does not exist, even though it appears to be symmetric around 0. Also, if you look at the variance formula, if you were to pick n is equal to 0, 1, or 2, you're either going to get a negative number, which doesn't work for variance, or dividing by 0, which doesn't work for anything. So this formula for variance usually is only taken as its definition when n is bigger than 2 and undefined otherwise, or defined to be other things depending on what you're trying to get out of it. All right, and also, if the degrees of freedom is t is equal to 1, you know, your distribution that looks like a t distribution, but its tails are so fat it doesn't have an expected value of 0, is sometimes called the standard Cauchy distribution. And I highly recommend looking at the probability density function for t, substituting 1 in for n, and seeing how that simplifies to get the actual proper definition of the standard Cauchy distribution. But that is how we derive the t distribution, and here's some of the important properties that you definitely need to know when you're working with it. Again, there are other statistical distributions that we'll get into in the near future, but I just wanted to present that here today. Hope you enjoyed this video, and I'll see you in the next one. Take care.